Hello, in this lecture we'll find out the length of tangent x. In the drawing we have a small circle that is inside this quarter circle A or B. In addition, we know that this is line segment OQ that is equal to 5 units in its length. This is tangent AEP. It is tangent to this small circle at point P. Point P is the point of tendency of tangent AEP with this small circle. And according to what is given as the question, AP equals to x, and we have to find out the value of x. That is, and to say we have to find out the length of tangent AP that is equal to x. So first of all, we define the center of this small circle. This point is point C. Point Q is the point of tendency of tangent OB with this small circle. So we join point C and Q together by a straight line. Point C is the center of this small circle. Point Q is the point of the small circle itself. This is exactly the definition of a radius. Therefore, CQ is the radius of this small circle. We define the radius of this small circle as A. So CQ equals to A according to our definition. This is the radius of this small circle. And because of the fact that the radius CQ is drawn to point Q, that is the point of tendency of tangent OB with this small circle, and whenever you have a radius that is drawn to the point of tendency, then tangent OB will be perpendicular to the radius QC. If OB is perpendicular to QC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. We define the radius of the big quarter circle as B. So OB is the radius of this quarter circle. That is equal to B units in its length according to our definition. OB equals to B. And the radius of this quarter circle is also AQ. So AQ is also equal to B units in its length. According to our definition, it is the radius of the big quarter circle. In the next step, we join point C and P together by a straight line. CP is of course the radius of this small circle that is equal to A units in its length according to our definition. Because of the fact that the radius CP of this small circle is drawn to point P, that is the point of tendency of tangent AP with this small circle, and whenever your radius is drawn to the point of tendency, then tangent PC will be perpendicular to the radius PC. Then tangent AP will be perpendicular to the radius PC. If PA is perpendicular to PC, it means that this angle equals to 90 degrees according to rule 1. In the next step, we join points A and C together by a straight line. By joining points A and C, you can do the right triangle. No?
שלום.
כן.
היי, מדברת דניאל מסקר, מה שלומך?
בסדר.
אני מתקשרת כי דיברנו השבוע לגבי
כן,
העסקאות.
דיברתי עם יסמין, כן, בסדר.
כבר עשית את זה?
אני לא יודע, אמרה לי שצריך עוד פעם להתקשר אליי בקשר לחיוב של פרטנר.
לא, אני מדברת איתך על סונו, על שער, מה שאמרנו.
זהו, אז צריך באמת לבטל את זה, אני לא יודע מה.
כבר ביצעת את זה אז?
לא. אני דיברתי עם יסמין, אבל בינתיים זה מופיע בחשבון, החיוב עדיין לא בוטל.
אין בעיה, אבל היא פתחה לך ברור?
כן, אבל
אוקיי, בסדר, אז זה בטיפול עכשיו.
אז
ובטיפול של מחלקת ביטחון, 5 מהעסקים יחזרו אליך. בסדר?
בסדר.
טוב, שיהיה לך המשך יום טוב.
דניאל, בקשר
כן.
לכרטיס אשראי, מתי הוא יגיע? אני פשוט אין לי אמצעי תשלום.
מה? הוא עד 14 מהעסקים אמור להגיע לך.
אני רוצה אפילו שזה יהיה יותר מהר, כי אין לי דרך לקנות
אם
דברים.
היא אמרה לך שהיא נסתה לזרז את זה, היא תנסה, אבל אנחנו
לא, היא לא אמרה לי, אולי תנסי לזרז.
אז עד 14 מהעסקים, זה בדואר. נשלח בדואר.
יכולה לעשות משהו את יכולה לעשות משהו בעניין, לזרז את העניין?
לא, ברגע שזה נשלח בדואר ישראל, אני איך לזרז את זה.
אז כמה זמן ייקח לה?
בין 7 ל-14 מהעסקים.
עכשיו תקוע בלי כסף, את מבינה? אין כסף, אין דרך לקנות דברים. הכל אני עושה בכרטיס אשראי, אין לי מזומן. טוב, תודה. שלום.
טוב, שיהיה לך המשך יום טוב.
שלום. So by joining points A and C together with a straight line, you can determine the right triangle APC. So I copy the right triangle APC in the new page and we will implement the Pythagoras theorem on this right triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here by PT is a variation for Pythagoras theorem. So actually, this is the right triangle APC that I quoted from the original drawing. This right triangle APC, AC square, that is the square of the hypotenuse, equals to AP square plus PC square. So I write it down. AC square equals to AP square plus PC square. So AC is the missing side, so really what it is, AC square equals to AP square. AP is x, therefore AP square is x square plus PC square. PC is a, therefore PC square is a square. So in total, according to equation 1, we shall find out that AC square equals to x square plus a square. Here we have an internal notch between this big quarter circle and this small circle. That is to say, they touch each other internally at this point. This is their touching point, so we define their touching point. This point is point K. So here we can implement rule 9 that talks about an internal match between two circles or semicircles. So I'll take quickly on rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together passes for their touching point. So in the drawing, we have two circles. This is the big circle, this is the small circle, and they touch each other internally at this point, point P. The center of this big circle is here at point O. The center of this small circle is here at point M. And the straight line that connects their centers together is of course the straight line OM. And according to this rule 9, the straight line OM must pass for their touching point, that is point P. Again, the straight line OM must pass for point P, that is their touching point. O and P is one straight line. Again, according to this rule 9, O and P is one straight line. So we can actually implement rule 9 in our drawing. So as I mentioned before, because of the fact that we have internal match between the small circle and the big quarter circle, therefore according to rule 9, the straight line that connects their centers together must pass for point K, that is their touching point. Point O is the center of the big quarter circle, point C is the center of the small circle, and the straight line that connects their centers together is of course the straight line OC, and the straight line OC must pass for point K, that is their touching point. Or OCK is one straight line. Again, OCK is one straight line according to rule 9. So we connect points O and C together by straight line, and the straight line OC that connects their centers together must pass for point K, that is their touching point. Or OCK is one straight line. And see here that the straight line OC that connects their centers together passes for point K, that is their touching point. So point C is the center of this small circle, point K is the point of the small circle itself, therefore CK is the radius of this small circle, that is equal to A units in its length according to our definition. And here point O is the center of the big quarter circle, point K is the point of the quarter circle itself. So this is exactly the definition of a radius. Therefore OK is the radius of the quarter circle, that is equal to B units in its length according to our definition. So OK equals to B, CK equals to A, and therefore OC equals to OK minus CK. Again, OC equals to OK minus CK. So I write it down. OC equals to OK minus OC. Again, OC equals to OK minus CK. Again, OC equals to OK minus CK. OK minus CK. Okay, again, OC equals to OK minus CK. So OC in total equals to OK. OK is B minus CK. CK is A. So in total, OC equals to B minus A units in its length. OC equals to B minus A units. So OC equals to B minus A units in its length. It is given us the question that OQ equals to 5 units in its length. So in the next step, we'll implement the Pythagoras theorem on this right triangle OCQ. So I copy triangle OCQ in a new page and we'll implement the Pythagoras theorem on this right triangle, triangle OCQ. Here by PT is the version for Pythagoras theorem. The hypotenuse OC equals to B minus A units in its length, and side CQ of the right triangle OCQ equals to A units in its length. It is actually the radius of this small circle that is equals to A units in its length. So actually this is the right triangle OCQ with the point from the original drawing. In this right triangle OCQ, OC squared, that is the square of the hypotenuse, must be equal to CQ squared plus QO squared. Again, OC squared equals to CQ squared plus QO squared. So I write it down. OC squared equals to CQ squared plus OQ squared. The hypotenuse OC is V minus A, therefore OC squared is B minus A squared, and it is equal to CQ squared. CQ is A, therefore CQ squared is A squared plus OQ squared. OQ is 5, therefore OQ squared is 5 squared, it is 25. So in total, according to equation 2, we actually found out that B minus A squared equals to A squared plus 25. Here, we'll open the brackets on this side of this equation, equation 2, and we get that according to this equation, equation 2, B minus A squared equals to B squared plus A squared minus 2 times A times B, and it is equal to A squared plus 25. So here we have A squared on both sides of this equation 2, so A squared will get cancelled. After we cancel A squared, in this side of the equation 2 we left only with B squared minus 2 times AB. On the other side of the equation we have 25. So in total, according to equation 2, we actually found out that B squared minus 2AB equals to 25. Well, according to equation 1, AC squared equals to X squared plus A squared. So in the next step, we will do a construction. That is to say, from this point, point C, we will draw perpendicular on AO. Again, from point C, we will draw perpendicular on AO. On side AO of the quarter circle AOB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AO. This point is point N. if I did this construction, we can do quadrangle NOQC. This is quadrangle NOQC. Inside this quadrangle NOQC, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 pieces angle. In total, they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 pieces angle must be equal to 90 degrees in its size. So inside quadrilateral NCQO, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be at least a right angle, if not a square. So we relate to this quadrilateral NCQO as a right angle because it has 4 right angles. So I'll write it down. This is quadrilateral NOQC. This is a right angle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle NCQO, side CQ must be equal to the opposite side NO. But CQ is A, therefore NO must be also equal to A units in its length. Likewise, according to the same rule, in the same rectangle NCQO, side NC must be equal to the opposite side OQ, but OQ is 5, therefore the opposite side NC must be also equal to 5 units in its length. So, what is the length of line segment AN? From the drawing, it is very easy to see that AN in total equals to AO minus NO. Again, AN equals to AO minus NO. So, I write it down. AN equals to AO minus NO. So AN in total equals to AO. AO is the radius of this quarter circle that is B minus NO. We just right now found out that NO equals to A. So in total, AN equals to B minus A units in its length. So see, this is line segment AN that is equal to B minus A units in its length. In the next step, I'll copy the right triangle ANC in the new page and we'll implement the Pythagoras theorem on this right triangle, triangle ANC. Here by PT is the operation for Pythagoras theorem. So actually, this is the right triangle ANC that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle ANC, AC squared, that is the square of the hypotenuse, equals to AN squared plus NC squared. So I'll write it down. This will be equation 3. AC squared, that is the square of the hypotenuse, is equal to AN squared plus NC squared. AC is the missing side, so we leave it as it is. So AC squared equals to an squared. An is b minus a, therefore an squared is b minus a squared plus nc squared. Nc is 5, therefore nc squared is 5 squared, it is 25. So in total, according to the equation 3, we can find out that ac squared equals to b minus a squared plus 25. So here we open the brackets on this side of this equation 3, and finally we get that according to equation 3, ac squared equals to b minus a squared. B minus a squared equals to b squared plus a squared minus 2 times a times b plus 25. We actually found out that according to equation 1, ac squared equals to x squared plus a squared. Therefore, we substitute ac squared in this equation 3. Substitute ac squared in this equation 3 by x squared plus a squared from equation 1. We do it now and we get that according to equation 3, ac squared is actually x squared plus a squared, and it is equal to b squared plus a squared minus 2 times ab plus 25. So here we have a squared on both sides of the equation, so a squared will get cancelled. After we cancel a squared, this side of the equation we left with x squared equals to b squared plus 2 times a times b plus 25. I repeat again, according to equation 3, we shall find out that x squared equals to b squared minus 2 times a times b plus 25. But according to equation 2, b squared minus 2 times ab equals to 25. Therefore, we substitute b squared minus 2 times ab by 25 in this equation 3, and we get that in total x squared equals to, again, b squared minus 2 times ab is 25 according to this equation 3, and we have here plus 25. So in total we found out that x squared, that is the tangent that we are looking for in this question, is equal to 25 plus 25, that is 50. Here we take a root out of this equation and finally we get that x equals to the square root of 50. 50 is 2 times 25, and the square root of 25 is 5. So in total this expression equals to 5 times square root of 2 units. 5 times square root of 2 is 7.071 units. So in total, if you found out that the length of tangent AP is equal to x, it is equal to either 5 times square root of 2 units, or in terms of numbers, the length of this tangent AP is equal to x is equal to 7.071 units in its length. Okay, so in the next step, I'll summarize the lecture. So in this lecture, our mission is to find out the length of this tangent AP is equal to x. Our mission is to find out the value of x. So in the drawing, we have this small circle that is inside this quarter circle AOB. In addition, we know that this is line segment OQ that is equal to 5 units in its length. And again, our mission is to find out the length of this tangent AP is equal to x according to what is given in the question. Actually, tangent AP is tangent to this small circle at point P. So, first of all, we define the radius of this small circle as A, and we join points A and Q together, but this is we defined this is point the center of this small circle is C. So this is the center of this small circle, that is C, and we join and we find the radius of this small circle is A. We join point C and Q together by a straight line. Point C is the center of this small circle, point Q is the point on the small circle itself, therefore CQ is the radius of this small circle that is equal to A units in its length according to our definition. And because of the fact that the radius CQ is drawn to point Q, that is the point of tendency of tangent OB with this small circle, whenever your radius is drawn to the point of tendency, then tangent OB will be perpendicular to the radius QC. If OB is perpendicular to QC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we join point C and P together by a straight line. Point P is the point of tendency of tangent AP with this small circle. Actually, AP is the tangent that we are looking for in this question. So CP is of course the radius of this small circle that is equal to A, and because of the fact that radius CP is drawn to point P, that is the point of tendency of AP with this small circle, whenever your radius is drawn to the point of tendency, then tangent AP will be perpendicular to the radius PC. If AP is perpendicular to PC, it means that this angle equals to 90 degrees according to rule 1. In the next step, we join points A and C together by a straight line, and we implemented the Pythagoras theorem on this right triangle, triangle APC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares from the perpendiculars. This is right triangle APC that are covered from the original drawing. AP actually equals to X, that is the tangent that we are looking for in this question. PC is the radius of the small circle, that is equals to A unit in its length according to our definition. So in this right triangle APC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, is equal to AP squared plus PC squared. AC is the missing side, so we have to see this. So AC squared equals to AP squared. AP is X, therefore AP squared is X squared plus PC squared. PC is A, therefore PC squared is A squared. So in total, according to question 1, we actually found out that AC squared equals to X squared plus A squared. In the next step, we implemented in our drawing rule 9. Because of the fact that we have an internal arch between this small circle and this big quarter circle, that is to say, they touch each other internally at this point. Whenever you have an internal arch between two circles or semicircles, so you can implement rule 9. We define the touching point of this small circle with this big quarter circle. This point is point K. The center of this small circle is at point C, and the center of this big quarter circle is at point O. And according to rule 9, if two circles touch each other internally, then the straight line that connects their centers together passes for their touching point. So in the drawing we have two circles. The center of this big circle is at point O. The center of this small circle is at point M. And the straight line that connects their centers together is OM, of course. Their touching point here is at point P. So according to this rule 9, the straight line that connects their centers together, that is OM, must pass for their touching point, that is point P. Or OMP is one straight line. Again, according to this rule 9, OMP is one straight line. So I can implement rule 9 in our drawing. In our drawing, we have an internal arch between the small circle and the big quarter circle. That is to say they touch each other internally at this point K. And whenever you have an internal arch between two circles or semicircles, you can implement rule 9. The center of this big quarter circle is here at point O. The center of this small circle is at point C. And the straight line that connects their centers together is of course the straight line OC. And according to rule 9, the straight line OC must pass for point K, that is their touching point. Again, the straight line OC must pass for their touching point, that is point K. OCK is one straight line. Again, OCK is one straight line according to rule 9. So actually join points O and C together by straight line, and according to rule 9, the straight line OC must pass for point K. And again, you can see here that the straight line OC is indeed passes for point K, that is their touching point. So point C is the center of this small circle, point K is the point on the small circle itself, therefore CK is the radius of this small circle, that is equal to limit in itself according to our definition. Point O is the center of the big quarter circle, point K is the point on the quarter circle itself, therefore OK is the radius of the big quarter circle, that is equal to B units in itself according to our definition. So OK equals to B, CK equals to A. Therefore OC must be equal to OK minus CK. OC equals to OK minus CK. Again, OC equals to OK minus CK. So OC in total equals to OK, that is B, it is the radius of the big quarter circle, minus CK, that is A, is the radius of the small circle. So in total, OC equals to B minus A units in its length. And the next step, we implemented the Pythagoras theorem on this right triangle, triangle COQ. So copy triangle COQ in a new page and implemented the Pythagoras theorem in triangle COQ. So actually, this is triangle COQ that I got from the original drawing. We just right now found that OC equals to B minus A, QC equals to A, this is the radius of the small circle, and OQ equals to 5, according to what is given as the equation. So in this right triangle OCQ, OC square, that is the square of the hypotenuse, equals to CQ square plus QO square. OC is B minus A, therefore OC square is B minus A square, and it is equal to CQ square. CQ is 8, therefore CQ square is A square, plus OQ square. OQ is 5, therefore OQ square is 5 square, that is 25. So in total, according to equation 2, we have found out that B minus A square equals to A square plus 25. Here we open the brackets of this side of this equation, equation 2, and finally found out that according to this equation, equation 2, B minus A square equals to B square plus A square minus 2 times A times B, and it is equal to A square plus 25. Here we have A square on both sides of the equation, so A square gets cancelled. After we cancel A square, in this side of the equation we left with B square plus 2B. On the other side of the equation we left only with 25. So according to equation 2, we shall find out in total that B square plus 2AB equals to 25. But according to equation 1, we only found out that AC square equals to X square plus A square. In the next step, we did a construction, that is to say, from this point, point C, that is the center of this small circle, we drew perpendicular on AO. Again, from point C, we drew perpendicular on AO. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AO. This point is point N. By doing this construction, we create this quadrilateral NCQO. Inside this quadrilateral NCQO, we have 1, 2 rectangles. This angle equals to 90 degrees according to our construction. This angle equals to 90 degrees because A of B is a quarter circle, and this angle equals to 90 degrees according to rule 1. So in total, inside quadrilateral C and OQ, we have 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the side of this 4 facing angle, in total they must be equal to 360 degrees, according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 facing angle must be equal to 90 degrees in its size. So inside quadrilateral NCOQ we have 4 rectangles, and according to rule 5, any quadrilateral that has 4 rectangles must be a rectangle, if not a square. So we relate to quadrilateral NCQO as rectangle because it has 4 rectangles. So quadrilateral NCQO is a rectangle according to rule 5. But you also know that the opposite sides of a rectangle are equal to each other. So an rectangle NCQO, sine NC must be equal to the opposite side QO. But QO is 5, therefore the opposite side NC must be equal to 5 units in its length. Likewise, according to the sum rule, in the same rectangle S, in the same rectangle, so this letter is C, in the same rectangle CNOQ, side CQ must be equal to the opposite side NQ, but CQ is 8, is the radius of the small circle, this is equal to A, but CQ is 8, therefore NQ must be also equal to M in its length. What is the length of this missing isolate AN? On the moment it is very easy to see that AN equals to AO minus NO. Again, AO minus NO equals to AN. AN equals to AO minus NO. So AN total equals to AO, that is the radius of the big quarter circle, this is equal to B, minus NO, that is equals to A. A is the radius of the small circle, of course. So in total, AN equals to B minus A. AN equals to B minus A. NC equals to 5 units in its length. And AC is the hypotenuse of the right triangle ACN. So in the next step, I copied the right triangle ACN in an equation to implement the Pythagorean theorem in this right triangle ACN. So okay, this is the right triangle ACN, that is the point from the original domain. We get AN equals to B minus A. So in this right triangle A and C, according to the Pythagorean theorem, AC square equals to AN square plus NC square. AC square equals to AN square plus NC square. AC is the missing side, so we leave this it is, so it is AC square equals to AN square. AN is B minus A, therefore AN square is B minus A square plus NC square. NC is 5, therefore NC square is 25. So in total, according to equation 3, we can find out that AC square equals to B minus A square plus 25. So AC square equals to B minus A square. B minus A square equals to B square plus A square plus 2 times AB plus 25. So here, according to equation 1, we have already found out that AC square equals to X square plus A square. Therefore, we can substitute AC square here by X square plus A square. We did it. And we can find out that AC square equals to X square plus A square according to equation 1. And it is equals to B square plus A square plus 2 times AB plus 25. So here we have A square on both sides of the equation. So A square we get cancelled. After we cancel X square, after we cancel A square. In this side of the equation 3 we left only with X square. On the other side of the equation we have B square minus 2AB plus 25. But according to equation 2, B square minus 2AB is 25. According to equation 2, B square minus 2AB is 25. Therefore, we substitute B square minus 2AB by 25. And total we found out actually that X square equals to, again, B square minus 2AB is 25 plus 25. So in total, X square equals to 25 plus 25, that is 50. X square equals to 50, we took out of this equation and found out that X equals to the square root of 50. 50 is 2 times 25. And the square root of 25 is 5, so in total this expression equals to 5 times square root of 2. 5 times square root of 2 is 7.071 units. So in total we should find out that the length of this descendant AP is equal to X. It is equal to either 5 times square root of 2 units. In terms of numbers, the length of this descendant AP is equal to X is equal to 7.071 units. Okay, thank you very much.